Other key is transmission delay is more significant. Make sense? The concept is important, but you understand that you need to drive the car. The packet actually need to go through the electromagnetic waves, goes through those actual physical channels. That's basically the propagation delay. Make sense? Only the scale wise is slightly different in this scenario. Okay?
So in total, the total amount of time it takes until the caravan's lined up before the second toll booth, 2 minutes, that's the transmission time, plus 60 minutes, that's the propagation time, for a total of 62 minutes. Having taken a deeper dive into propagation delay, let's next take a closer look at queuing delay. And we want to get both a qualitative and a quantitative feel for queuing delay. So to do so, let's define A as the average packet arrival rate and L as the length of a packet. So L times A is the arrival rates of bits to that link. As before, R is the link bandwidth, that is the transmission rate of bits. Now, if we take the ratio of these two quantities, the arrival rates of bits divided by the transmission rate of bits, we get a quantity that's known as the traffic intensity. That's the ratio of the amount of arriving work, if you will, the bits, to the system's capacity to do that work, that is, transmit the bits. And we all know intuitively that when the traffic intensity is low, that is, L times A over R is small, there's seldom a queue. And when L times A over R is greater than 1, there's more work arriving on average than the system's capacity to do that work. And so in this case, delay is infinite. The queue of backlog work just gets larger and larger and larger over time. The graph here shows the average queuing delay as a function of traffic intensity. And note when the traffic intensity gets close to 1, delays get very large, very fast. And you're certainly used to this kind of phenomena on roadways. It's exactly analogous here, except that we're interested in a communication network instead of a roadway, and packets and bits instead of a car.
No, they're implementing another work platform.
Throughout this course, we're going to use the live internet to illustrate and study the principles that we're learning. Well, we've learned about delay, and there's a tool called traceroute, which will actually allow us to measure and inspect what's happening in terms of delay on a path from a source to destination. Let's take a look at traceroute. Traceroute is a program that runs on your laptop or computer. It provides live measurements of packet delay from the sender, your computer, to routers along a path towards a destination. Traceroute works as follows. It first sends 3 packets to the first hop router. The first hop router sends a reply message in response to each of these packets. The traceroute sender measures the round trip time, the RTT, from when it sends a message until when it gets the reply, and then displays those 3 RTT measurements. It then sends 3 packets to the second hop router, measures and displays the RTT to the second hop router, and continues on until the final destination is reached. Let's take a look at what the output of a traceroute looks like. This is the result of a traceroute I performed earlier from gaia.cs.umass.edu in Amherst, Massachusetts to eurocom.fr in France. And let's take a look at this trace in detail. Traceroute first sends 3 packets from Gaia to the first hop router on the path to eurocom.fr. That first hop router is in the computer science department network, and the measured RTT delays are 1 millisecond, 1 millisecond, and 2 milliseconds. Traceroute then sends 3 packets from Gaia to the second hop router, which is still inside the UMass network, pretty close to the first hop router, and the RTT delays are again around 1 millisecond, 1 millisecond, and 2 milliseconds. If we go a little bit further down in the traceroute, we see a 22 millisecond RTT delay to a UK router in Washington, D.C. And then we next see an RTT of over 100 milliseconds to a router in the Géant network. That's a research network in France. And if you look at the difference between 22 milliseconds to get to DC and 105 milliseconds to get into France, you see the effects of propagation delays across the Atlantic Ocean. Sometimes the measured RTT decreases even though packets travel further, as we see here, and that's possible because the congestion level, the queuing delay upstream, can change over time. Lastly, we'll sometimes see stars, and this is from a router that refuses to reply to a received traceroute message from the source, and so an RTT measurement can't be made. This is mostly just a review slide. We've been focusing on packet delay, but we need to remember that packet loss can also occur when router buffers fill up and an arriving packet has no place to be stored. In high congestion scenarios, losses can be high. I've measured times when 10 to 20% of my packets are being lost. In Chapter 3, we'll see that there are a number of techniques that hosts can use to detect and recover from packet loss and to control the rate at which they're sending to control congestion. The final performance metric that we want to spend some time on is known as throughput. Throughput is the rate, bits per second, that are being sent from a sender to a receiver. And throughput now also needs to be defined over an interval of time. It could be instantaneous or over a very short period of time, or it could be averaged over a much longer period of time. And to think about throughput, it's often useful to think about water flowing through pipes. You can tell I love analogies. You can think of a sender as sending fluid into a pipe at some rate, and each transmission link along a path is being able to carry fluid at some rate. Some pipes are fat, some pipes are thin, and here's what you want to think about. When an end-to-end flow carries packets over multiple pipes serially, how does the capacity of each pipe, the maximum rate at which a pipe can carry a fluid, determine the overall end-to-end throughput that a flow receives? And let's think about this in the context of this scenario here, where a sender is sending a large file to a receiver over 2 hops through 2 links. Let's look at a couple of examples. In this first scenario, we have a thin pipe with capacity R sub S, S is for server, followed by a thick pipe with a higher capacity R sub C, C is for client. The end-to-end throughput here will be limited to R sub S, the capacity of the first pipe, the thin pipe. In the second scenario, we have a fat pipe with larger capacity R sub S, followed by a thinner pipe with smaller capacity of R sub C. The throughput here will be limited by the capacity of the thinner pipe, in this case, R sub C. And in general, when you think about the throughput that a source-to-destination path can receive, it's going to be limited by the capacity of the thinnest pipe, the pipe with the smallest transmission capacity. In networking, this link is sometimes known as the bottleneck link.
This is what Ivy League universities you can get into with a 3.6 GPA. 90%.
And lastly, we need to think about how individual flows are going to all interact with each other inside the network in terms of their achievable throughput. So take a look at this diagram here. What you see is we've got 10 servers and 10 clients and a single connection from each server to one of the clients. Now, the links at the edge of the network, let's just assume that they're dedicated. But somewhere in the center of the network, we've got a shared link of capacity R. Now let's also assume that this shared link of capacity R is able to fairly share the bandwidth available among the 10 flows so that each sees a bandwidth available of R over 10. What is the per connection throughput in this particular scenario? Well, think about this in terms of pipes again, where each session now passes through 3 pipes, seeing a capacity of R sub S, R divided by 10, and R sub C. Remember, that middle link is going to be shared by 10 sessions, so each session only gets 1/10 of the capacity. Well, hopefully you can see that the per connection end-to-end throughput is going to be the minimum of these 3 values, R sub C, R sub S, and R divided by 10. And you might be interested to know that in practice, R sub C or R sub S is generally smaller than R divided by N. That is, bottleneck links tend to be at the edge of the network. In this section, we took a deeper dive into 2 aspects of network performance, delay and throughput. In the case of delay, we identified 4 components of delay: processing delay, queuing delay, transmission delay, and propagation delay. And we used traceroute to look at some real delays as measured in the internet. And we also took a look at throughput. And hopefully there you found the analogy between fluids and pipes to be interesting and useful.
Okay, now you can do your quiz number 2, okay? After you're done, you can have a break. So we will be back 6:10. I will have you another quiz like we have upstairs.
Another quiz?
Yes. Another one. bit short, but I need to copy those to get those ready. So we'll work on this one. So when you're done, just go to break naturally. So we'll be resume at 6:10. Make sense? What? I'm going to give you a second kids again. It's just one more second kids. So what's the question? You wanted that first picture? Oh, it's not really. Later on, you'll find your friend. You can copy them. I'll give you a first place now. This is my first one. I know this is your first one, but give her. I have one extra copy. Give her. I didn't give you, so we have two new students. So I only have one extra copy. I will try to. By any chance you have your first quiz, I will copy one for her.
Oh, I did write down my name. Is that okay?
It's fine. It's better than I do. I will copy one for her. Only seconds. Guys, when you're done, just break, okay? Then remember this section is important. Then you can go. I'll just get your next quiz ready. that's for the case number 1. Okay. Thank you. You too, if you later need, you can talk to your friends regarding to solution for the case number 1.
Okay.
Or you can find.
Okay, thank you.
naturally. Okay. Put that. Not that. finished, right? No? It's fine. We'll work together later. That means you need to read book for your homework. Okay. Do you guys need a 5 minutes break? Then we will quickly discuss together.
Okay.
Yeah. If I will come back, also I will count all those finished. You guys should finish.
Last was previously. I just want to.
I don't.
Guys, homework is on e-course, okay? It will be next Monday. You guys need to finish your chapter 1, okay?
We can take it too. We are taking this home to do.
Say again?
Can we take this?
We take it home.
Do we need to submit it?
No, you don't need. We will discuss together. Just then 5 minutes break, we will discuss together.
Oh, okay.
It's the quiz is the kind of the process how to absorb what we just learned. Otherwise, you guys are pretty happy when you watch the video, right? You know my point now. When you watch the video, you actually need to watch what you think, not like happy to check your phone. But you guys are good. I'm just saying you guys are not checking your phone. Means when you watch, it's basically you need to. After you watch, you should get done to do this. Make sense? 5 minutes we will discuss. Okay.
Calculation is what because when they were answering, I don't know. Did you finish? Then finish. What she was going to do was ask him. How is it? How is it?
How is it?
Yeah. It's nice. You answer that question very well. So I will see you after.
I don't understand.
Those you always think kind of open stage.
and been a lifesaver with my application and helping you.
Could you call everybody in? Well, a longer break. Yeah, you have a question, you can ask.
I don't understand that still.
Okay. Just a second. Basically, the thing about it, when I send yourself your account, right? When I send you something, I send your first pack in the rapid, think about books. And I push the first car out when you first pack it after your first boost. Then the boosters have nothing to do. They don't process the car. The kids process and send it out. At my time, I can process second car. Yeah. Basically, see, the first packet, I send it out. This is the first time using it. After first time using it, the car is there. Right? That's the first car. Then at the second time, yes, I can process second car. But here, the second one, I also do. Makes sense? Then at the second time, you use the second car. This car is already there. Third time, you use the second, this is oh, okay, including the timeline. Basically, first, at the second time, you need the first package. At the second time, you need the second package. Then at the third time, you need the second package. Makes sense? Basically, it's not about to wait the first packet all the way around the destination. You start sending out the second package. That's basically your thing. That's why I asked you. Because in the homework, there's more than makes sense? So, the package out of the personal hubs. How about how many hubs for each packet? For example, you have 2 hubs, you need 2 you have 3 hubs, 3 hubs. For one packet, that's very useful. But when you add another packet, still you only need to add 1 packet out of every hub. Because everything, they are independent. They are processing those.
Okay, so
you don't remember anything, but you need to go back to the timeline concept. Makes sense? Then you need to actually think through because I can remember. You need to think through actually what is happening. Every package is independent. Make a car, you have 2 cars. One car goes to the road, the road can have a car. This car. Makes sense? They can handle the car Guys, you guys ready? Everybody in?
No.
So guys, just in case, okay, I don't think for the history section is important. Along years what happened? You guys actually can search all those links by yourself, but just consider the time. I don't think we have time to watch the history part. Maybe I will ask to watch the security part. Makes sense later. The history, the link, I just put it there. Just hope I may, come back next time and ask questions. Joking. Okay, let's start. So, although we have like 15, 16, it's still changing. I don't know how many. So still consider a small class, right? So if you have questions, just directly jump out and ask. Okay, make sense? I still want if you have questions, just directly ask. Guys, first one, routing versus forwarding. We explained a lot, right? For this one, should be easy. Which should be the answer? A. Forwarding is local, routing is global, right? You also should know actually what's happening there. So for the second one, remember, when we talk about packet switching and circuit switching, so sometimes this part actually is the tricky part. It's not a single answer, it's a multiple answer. Make sense? I think that's basically make it a little bit trickier. So in that case, is A right or wrong?
Right.
Because I highlighted we are talking about packet switching, right? So resources are used on demand for packet switching, make sense? And circuit switching is you need to be reserved, okay? Is second one right or wrong?
Wrong.
So even current phone network is not based on the circuit switching. The old phone, just keep saying, right? Okay. How about third C?
Right.
Congestion loss and the variable end-to-end delay are possible with the technique. So basically for this one, think about for each packet. I keep saying each packet is independent, right?
Yeah.
When this router processes this packet, the second router, they can handle different packet. Makes sense? Each router, they're independent. So in that case, think about it. When I have multiple packets from sender to receiver, each packet is independent. Makes sense? Basically, when each packet, they might go through different route. Depending on at that time instant, what is the network situation? Make sense? For later packet, maybe some network got congested. So later packet may pick another route. Okay, make sense? In that case, the congestion loss and the variable entity are all possible for the packet delay part. And the why? The computer apparently is not that friendly. Okay. So what else, guys?
D. G. E. No, E.
E as in add, right?
Yes.
So data may be queued before being transmitted due to other users' data also queuing for transmission. Remember, guys, for the packet switching, basically it's sharing, right?
Yeah.
The sharing part, of course, could happen, right? What else?
G.
And the internet is used based on this packet switch, okay? So in that case, we have 4 choices for this one, okay? So next one, basically, is circuit switching. That should be relatively easy, right? What should we pick?
B.
So how do we separate the different channels? The video mentioned FDM, frequency division multiplexing PDM. We also have CDM. We also have other kind of multiplexing. Okay. What else?
C. D.
Who keep saying C?
No, it's not.
No, it's D.
Nobody saying C. B is just in the dog. Okay. What else? F. Because those questions are complementing to each other. Okay.
Yeah.
Makes sense. So these are 3 choices for this one. And for question number 4, what do you guys pick?
70.
So in this way, actually the tricky part is asking you the maximum number, right? Makes sense? In many cases, for example, I need from A to C, I need to use 2 channels, but I'm occupied 2 sub-channels. In that case, they may not be the maximum number. In all the maximum number, basically A to B, B to C, and I only have the 1 hop communication. Makes sense? That's the maximum number. That's you add 20 plus 19 plus 15 plus 16, which is 70, because it's asking maximum number. Makes sense, right? And question number 5, what do you guys pick?
A, B, and D.
You like A? In general, although this is kind of confusing. We will not say that internet is one network. We like to say it's network of
Network of
networks. Makes
networks.
sense?
Yeah.
In general. So basically, we will pick is made up of lots of different networks that are interconnected to each other. Okay, then is focused or not because it's multiple network. Makes sense. So this one we will take the B and the D. Okay. Remember, internet is we have so many networks. Why internet is powerful? Just connect them all together. Okay. Okay. 5 then. So 6. 6 is interesting, right? So we have 3 choices. Scenario: 5 users being multiplexed over a channel of. So basically, we have 5 users, and the channel bandwidth is 10 megabits per second. Okay, and the various scenario match the scenario to whether circuit switch or packet switch is better. Basically, that's the keyword. Which one is better? Okay, make sense? For the first scenario, each user generates traffic at the average 2.1 megabits per second, and the generated traffic at a rate, basically maximum rate could be 50 megabits per second when transmitting. The average rate is 2.1. So this one, for 1, you pick what? A, C.
B. For one, B. Okay. B. Neither works. Neither works well.
Who picked the B? Who want to?
I pick B. C. No, I pick B.
I'm asking who picked Israel. Do you mind explain a little bit why B?
So I chose B because for circuit switching, it's if I use 5 users and 10 megabits, so it should be 2 maximum per user. But in this case, it's already showing me 2.1, so it's more than that. For packet switching, I'll be looking at much more users than 5 using this bandwidth. So in either case, none of them works for this particular scenario.
So for this one, what's the keyword here? So basically, for this one, we have a 10 total bandwidth is 10 megabits per second. We have 5 users. Basically, in average, each user maximum available bandwidth for you is 2 megabits per second. In this case, you see one of the keyword is average. If your average rate, each user, the average rate is already 2.1. That's the point here. So basically, no matter is a packet or circuit switch, can we make this scenario? It's the overall capacity. Makes sense? Because this is the average is 2.1. We can handle some kind of peak is higher, but if you play the probability game, it's okay, right? We just wait a little bit longer. But if average is higher, what we can support, that's basically why we pick the B, neither.
Yeah.
Got it? Basically, it's over capacity, the network has support.
Yeah.
Okay, so far B, okay, just remember. Next one, each user generates traffic at 2 megabits per second, and the generated traffic at the rate of 2 megabits when transmitting. You guys pick the
Circuit switch.
C, raise your hand. Who want to explain why pick the C?
Okay, so because the average rate is 2 Mbp and we have 5 users, so since it is 2 times 5, that's 10. So
yeah, it can handle this. Yeah. So guys, so eventually you need to ask you the difference of packet switch and circuit switching, right?
so it's dedicated.
So packet switching is good for what kind of traffic?
For sharing.
For sharing.
For sure, what kind of traffic?
Sharing packets.
Bursty, right?
Bus.
Makes sense? Packet switching, why is work? Because it's good for the data traffic, and typical data traffic is bursty. Basically, you're not using the access channel at the steady rate all the time. Make sense? If for that kind of characteristic, basically, I need to occupy the traffic at the same rate along all the time. In that case, that is good for what application? Circuit switch application. Because in this case, I highlight both average and the peak rate, both are 2 megabit per second, right? It's like when I connect to the phone network, just keep chatting. That's basically what phone for, right? But for the data, the different story. Make sense? You basically think about what is a certain switching good for. That's why multi is better for, because this case. Make sense? Then the next one. So two will pick what? C, circuit switching. Okay. 3, each user generates traffic at average rate is low, but the peak rate could be high. Make sense? In that case, we will pick packet switching. Got it, guys? Perfect. Okay, so question number 7. Remember, currently we talk about the delay, right?
Yeah.
And the delay, actually, so far the delay we are talking, you have 4 different delays. That's the basic definition of 4 different delays, right? That's, for example, I have a packet, right? I send a packet, not a packet, I'm sending an email to Israel. I have 2 hops in the middle, okay? If this is a scenario, how do I calculate the delay? My point here is, in this case, when we talk about the definition of 4 different delay is only a what?
Excuse me.
1 hop, 1 nodal delay. Make sense? If I want to send a packet to Israel, I have 2 hops. Actually, each node, you need to consider the 4 different delay. Make sense? That's my point. You need to consider the big picture here. Remember, when we move on to the later chapter, we have the time we call RTT, right? What is RTT? Round trip time. Round trip. I send a packet to Israel, Israel return me back. Remember, round trip time. In that case, I need to send hop 1, forward to hop 2, forward to the receiver, then back. Here, I just want you to know. I don't know. It must all those are not very right. I cannot use short time. Okay, so basically this is an all nodal delay. Okay, that's my point. Okay, first one. Time need to perform integrity check.
Processing.
It should be processing delay, right? And time spent waiting packet buffer.
That's queuing delay.
Queuing delay. And the time spent transmitting packet into the link.
Transmission delay.
Transmission delay. And the last one is propagation delay. Okay, perfect. You guys are getting better. Then later lots of calculation here, right? For this one what's asking? What is the transmission delay for this packet, right?
Yes.
Which is easy. Will be L divided by R, right?
Yeah.
And the L, remember, only thing is, remember, here is a bytes. 1 byte is 8 bit. So in that case, it should be 1500 multiplied by 8 divided by 1 gigabit per second. Make sense?
Yes.
That's the only thing. Then after you do the calculation, should be B. Okay, guys? Should be B. Everybody agree?
Yes.
Then the question number 9. In this case, is what is the transmission delay for this packet? Still L is what? 1200, right?
Yes.
Should be 1200 multiplied by 8 divided 100 megabit per second. Meg is 10 to the 6. Makes sense? Giga is 10 to the 9. Okay. In that case, this one should be should be A. Okay, just get used to those basic calculations. Still, we are talking about what? Transmission delay.